torque acting on a dipole placed in an electric field. Now, say this is an electric field. This is an uniform electric field E. The lines are parallel and equidistant. And in this electric field, you have a dipole of dipole moment P making an angle theta with the direction of the electric field. Now dipole moment go from minus q to plus q. Electric field goes from positive to negative. Minus q is pulled downward with a force QE. Now what is E? E is the force on one coulomb charge. So the force on charge Q will be QE. Similarly, since this is negative, this minus Q will be attracted upwards with a force QE. Now two equal and opposite force, they create a couple. And this torque can be written as, if this is the direction of the force, torque is any one of the force and the perpendicular distance between the two forces. Now this angle is 90 degree. If this is theta, this is theta. Length of the dipole is twice L. Length of the dipole is twice L. Now, if this is 2L, this is theta, then this side is 2L sine theta. So what is the torque acting on the dipole? Torque acting on the dipole is equal to force into perpendicular distance between the two forces. So that is F. And what is the perpendicular distance? 2L sine theta. Now what is force? Force is QE. E is the intensity. So force is QE into 2L sine theta. So this becomes twice QL into E sine theta. Now twice QL is P. So torque becomes PE sine theta. Now what is P here? P is the dipole moment. Which is product of the charge and distance between the two charges. Q into 2L. So it is twice QL is P. So this twice QL is P. Torque is PE sine theta. Now P is a vector quantity directed from negative to positive. And intensity is also a vector quantity. And theta is the angle between P and E. P vector and E vector. So this can be written as torque equal to vector P cross vector E. This is a very, very important derivation. Now, if this derivation comes in the exam, you will be asked to define electric dipole moment P from here. So, electric dipole moment, how can you define from there? Now, what is the formula for torque? Formula for torque is PE sine theta. So we can write torque is equal to PE sine theta. Now if we take the electric field as unity, if electric field is of unit intensity, if electric field is 1 and if theta is 90 degree, what is theta? Theta is the angle between the axis of the dipole and the electric field. If theta is 90 degree, then torque is equal to P into 1, sine 90 is 1, then torque is equal to P. So from here we can define electric dipole moment as electric dipole moment is numerically equal to the maximum torque. Why the torque is maximum? Because theta is 90 degree. When theta is 90 degree, then torque is maximum, because maximum value of sine theta is 1. So electric dipole moment is numerically equal to the maximum torque experienced by it when placed in a uniform electric field. The lines of force are parallel and equidistant, so field is uniform. Uniform electric field of unit intensity with its axis perpendicular to the field lines. Theta is 90 degree. With its axis perpendicular to the field lines. So if this definition comes, what are the keywords? Electric dipole moment is numerically equal to the maximum torque. Why maximum torque? Here theta should be 90 degree. When placed in the field should be uniform. Field should be uniform. It should be E here and E here also. So throughout the field should be uniform. Electric field value should be 1. E should be 1. E should be 1. And theta should be 90 degree. Its axis should be perpendicular to the field lines. So torque acting on a dipole when it is placed in an uniform electric field is Pe sine theta or P cross E. And dipole moment can be defined as numerically equal to the maximum torque experienced by it when placed in an uniform electric field of unit intensity with its axis perpendicular to the field lines. Work done. In rotating a dipole. In an electric field. See children, I have an uniform electric field. Uniform electric field means the lines of force should be parallel and equidistant. This is my electric field. Say here is a dipole. This is minus Q. This is plus Q. Dipole moment is P, making an angle theta with the electric field. Electric field goes from positive to negative. What is the torque acting on the dipole? Torque is Pe sine theta. Now I want to rotate this dipole due to an external torque. I want to rotate this dipole. Now the work done by the external agent is variable. Why? Because as soon as you increase this angle from theta to d theta, this angle will change. So this torque is a variable torque. It is a variable torque. It is not constant. So when the force is variable, only one option left for you to find the torque is to integrate. Therefore, the work done by the external agent to increase angle from theta to theta plus d theta is dw, that is torque, into d theta. Now what is my torque? Torque is P sine theta. Into d theta. This is the small work done in rotating the dipole to an angle d theta. Now suppose you want to find out the work done in rotating the dipole through an angle theta, then you have to integrate this from 0 to theta. Now this is PE, and if you integrate sine theta, it is minus cos theta. Limits are from 0 to theta. Upper limit minus lower limit. So it is minus cos theta minus of minus cos 0. Now cos 0 is 1. So this becomes PE into 1 minus cos theta. This minus and minus becomes plus. So it is 1 minus cos theta. This is the work done in rotating the dipole through an angle theta. So the work done in rotating the dipole depends on theta, dipole moment, and electric field. So work done depends on theta, dipole moment, and electric field intensity. So it depends on P, E, and theta. So when you rotate the dipole, the problem is here the torque is a variable torque. So we assume that we rotate this dipole through a small angle d theta, and d theta is so small that within this small angle d theta, torque remains constant. So my small work done is torque into d theta. We assume that within this d theta angle, torque does not change. Now we substitute the value of torque as Pe sine theta, and then we integrate it from 0 to theta. We get the total work done in rotating the dipole through an angle theta. Now we see from the final expression that work done depends on dipole moment, electric field intensity, and the theta, which is angle between dipole moment and electric field. Potential energy of a dipole Potential energy will be denoted by capital letter U. First, let us find out potential energy of a dipole. Potential energy of a dipole when angle between dipole moment and electric field, angle between P and E is 90 degree. Say for example, I have a uniform electric field and the dipole is brought. The dipole makes an angle of 90 degree. This is the dipole moment. This is minus Q plus Q. When the dipole is brought from infinity to this point, say potential energy is the work done in bringing the dipole from infinity to this position. Now, the work done to bring minus Q charge is equal and opposite to the work done to bring plus Q charge. And what is my total work done? It is 0. So in this case, potential energy at 90 degree is equal to the work done, which is equal to 0. So potential energy at 90 degree is 0. Since potential energy of a dipole in an electric field is a sum of potential energies of minus Q and plus Q. Now, work done in bringing plus Q charge from infinity to the point is equal and opposite along the field line. When you bring the dipole from infinity along the field line up to one end of the dipole is equal in magnitude, is equal and opposite, is equal in magnitude but opposite in sign in work done to bring minus Q. So work done to bring plus Q from infinity to this point is along the field line is equal and opposite in sign in work done to bring minus q. So my total work done is 0 when you bring this dipole from infinity to this point. Along the field line, your work done is 0. So when we are bringing the minus q and plus q from infinity to this along the field line, work done to bring plus q is equal in magnitude and opposite in sign to bring minus q. So my net work done is 0 and net work done is potential energy. So when the dipole moment makes an angle 90 degree with the electric field, my potential energy is 0. Now case 2. Potential energy of a dipole when the angle between P and E is 0 degree. Now, potential energy at 90 degree can be written as potential energy at 0 degree plus work done in rotating the dipole through 90 degree. That means initially at 0 degree it has some energy plus some work is done in rotating to 90 degree. Both the energies are added up to get U90. But U90 from above is 0. That is equal to U0. Now what is the formula for work done? Work done was PE into 1 minus cos theta. What is theta? 90 degree. I have rotated the dipole through 90 degree. So here my work done is PE 1 minus cos 90. Cos 90 is 0. So what is U0? This is U0 plus PE. Therefore, U0 is minus PE. Now, if you can analyze it in a diagram, say, this is my electric field. It's an uniform electric field. And now the dipole makes an angle of 0 degree with the electric field. That means the dipole is parallel to the electric field. This is my dipole. This is my dipole moment of length 2L. It is parallel. This is minus Q. This is plus Q. It is making an angle of 0 degree with the electric field. Here theta equal to 0. Now, when you bring this dipole, say from infinity to this point, say this distance is x, minus q is brought forward an extra distance. Minus q is brought forward an extra distance. From infinity, it has come across an extra distance. So my total distance is x plus 2L. Minus q has come inside an extra distance of x plus 2L, while q has come a distance of x. So what is my potential energy is my total work done. Now to bring q charge, if it is QE into x, to bring minus q charge, my work done is minus QE into x plus 2L. So this becomes QEX cancels. So this becomes minus QE into 2L. This is Q minus Q into 2L into E. Q into 12 is nothing but P. So this becomes minus PE. Now tally, it is the same. It is the same. Now in general, if you're asked, what is the work done or what is the potential energy of a dipole when, or what is the potential energy of a dipole for any angle theta, for any angle theta between P and E. Now, potential energy at any angle theta can be written as initial potential energy at 0 degree plus work done in rotating the dipole through an angle theta. Therefore, U theta can be written as, what is U0? U0 is minus PE. Put the value of U0 here. Minus PE. What is my work done? This is the formula for work done. PE into 1 minus cos theta. So, PE cancels. If you open this bracket, PE will cancel. So what you have here? Minus PE cos theta. What is theta? Theta is the angle between P and E. So this can be written as minus P vector dot E vector. That is the potential energy of the dipole at any angle theta. So potential energy of a dipole when the dipole is at 90 degree with the electric field is 0, because potential energy is nothing but work done. And while you bring the dipole from infinity to this point, the work done to bring plus q is equal in magnitude but opposite in sign to bring minus q. My net work done is 0. So my potential energy at 90 degrees is 0. Potential energy at 0 degrees minus PE, because U90 is U0, initial potential energy, plus work done in rotating through 90 degree. Now U90 is 0 from top. Work done is PE into 1 minus cos theta. Theta is 90 degree here. U0 is minus PE. Now potential energy of a dipole for any angle theta between P and E is initial energy plus work done in rotating through theta. This is my initial energy minus PE. Work done is PE into 1 minus cos theta. So this becomes minus PE cos theta or minus P dot E, a very, very important expression for potential energy. And from here we see that potential energy is minimum when theta is 0, while maximum when theta is 180 degree. Theta 0, potential energy is minimum. From here we can say, if you can write over here, what is my potential energy? Minus P dot E. So you can come to a very, very important conclusion that potential energy is minimum. Potential energy is minimum when theta equal to 0 degree. That is, U becomes equal to minus PE. It is the minimum energy, and this represents the most stable equilibrium condition. of the dipole. And when theta is 180 degree, potential energy is maximum. Cos 180 is -1. So potential energy becomes PE. And when potential energy is maximum, this represents unstable equilibrium. So when you have an electric field, this is an electric field. Electric field goes from positive to negative, and you have a dipole making an angle of 0 degree. This is the dipole, minus Q plus Q. This corresponds to the stable equilibrium because electric field go from positive to negative. Positive will attract the negative and negative will attract the positive. So this is the most stable, and when you reverse the dipole making an angle 180 degree, then plus Q will come down, plus plus will repel, and that will be a case of unstable equilibrium.